last class we were looking at the view factor problems. The last problem which we took up in yesterday's class looked like a relatively simple problem. There is a circular tube or a pipe, okay. Outside there is a concentric pipe, but you have taken only half, okay. So only the semicircle we have taken. So the bottom is open. We wanted to get all the view factors. So we connected the bottom and called it 3. So now there are 3 surfaces. We started out with our view factor algebra. Now as far as 1 is concerned, there is no self view factor, f11 equal to 0. Now 1 to 2, if you look at 1 to 2 or 1 to 3, 1 to 2 and 1 to 3 there is no preference, it has the same thing, therefore f12 must be equal to f13. So I put some rule. If you apply the some rule for surface 1, you get this f11 equal to 0, f12 equal to f13 by symmetry, therefore f12 equal to 13 by symmetry, therefore sum is 1, therefore f12 is equal to f13 equal to half, there is no problem about this. Now a1 f12 equal to a2, reciprocal rule. From the reciprocal rule you get that f21 is r1 by r2, correct. This f21 must also be equal to f321, correct. So far so good, there is no problem. Now let us write the view factor matrix. The view factor matrix, there are 3 surfaces, 3 square 9 view factors are there, it is like this. So first row we are able to fill up 0, half, half. Second row we have got r1 by r2, f22 I do not know, f23 I do not know, right. f31 is also the same as f21, r1 by r2. Now I can say f2 to 3 by symmetry, f2 to 3 is the same as f3 to 2, correct. So instead of f3 to 2 I wrote f2 to 3, and then f2 to itself is the same as f3 to itself, okay. So there are 2 unknowns, f22 and f23, right. That is it, we are stuck here, we cannot proceed any further. With view factor algebra, this is the maximum we can achieve. So I must tell you that I am equally surprised that such a simple problem, it is not possible for us to, because I have not taken from somewhere. Yesterday on the spot I thought we will work out a simple case, and I am completely surprised that we are not able to solve it using view factor. But let it be there, so we cannot let it be like that. So we cannot underestimate, just because there are only 2 surfaces. Now there should be some way you have to take cos theta I, cos theta j, di, daj, and you have to integrate by counter integration, you can get it. Of course there are some asymptotic limits, that is when this r1 is very small compared to r2, then we can make some limiting assumptions, then f2 to 3 to itself will be equal to 1 and so on, you can proceed like that, okay. But right now no further progress is possible, okay, fine. So let us leave it at this stage. That is all, we can't get all the view factors, we can get some view factors, okay. Let us solve another problem. There is a surface like this, it is enclosed by a hemispherical, not hemispherical, semicircular disc, this is 1. Okay. Now get all VFs. No, if I get 1 I can use that some rule and break it down. Symmetry. You are not able to see the other one, Vikram. I wrote F32 as F23. Are you able to see that? Hmm. No, no. Even if areas are different, then more unknowns will be there.
Like it's just same as the reciprocity rule where area is same.
You are not understanding me. If you get one of the view factors, it's done.
You can't solve beyond that.
No, we are studying here because two equations are same. No, the two sum rules are same.
No, even otherwise it is not. There is one which is there will be one which will trouble you. You try.
We have just two equations and two variables, but both equations are parallel.
Mm.
So we cannot solve it.
So if you have 3/4 we can solve. Let us try something like that. Next problem we will do. But right now it is over, it is gone. This problem is gone, it cannot be solved. Okay, let us do this now. This one is pretty straightforward, isn't it? F11. What they are trying to say is, if A2 is not equal to A3, then you can solve it, or that is not his he is saying that more equations are required. I do not think this.
Rule same as like saying A1 equal to A2 and hence they are like if you see if you
No, why are you complicating it further? Is this correct or not? If I get one view factor, is the problem over? That is what I am saying. What else is there in this problem?
much like that.
No, whatever, if you take that, you will get some mind.
You get 2, sir.
Yeah, that is what. Out of the 2, 1 if you get, you can break down. You can break down, okay, because there is an additional rule. His question is, what are the total number of view factors? 9, okay. How many sum rules? 3. How many reciprocal rules? 3, okay. Then self view factor 1, self view factor only 1, F11 is 0. So 9 minus 7, 2. He says he is arguing that so 2 independent view factors have to be obtained. Why are you saying 1? But I have an additional thing, A2 equal to A3 and the geometric orientation is such that the view factor between 2 and 1 is same as 3 and 1. That is an additional information which I cannot simply get by n minus n into n minus 1 by 2, right. I can use my domain or knowledge of the geometry to reduce the number of view factors, okay. Is that point clear? That was a valid doubt. Everybody through with this? Okay. Now this problem is, don't worry that every problem will give rise to trouble and all that. These problems are solvable. F11 plus F12 equal to 1. What is this fellow F11? Yeah, he is 0. Therefore, F12 is A1. Okay. What is A1? Unit depth. Yeah. Please note that we are solving only 2-dimensional problems. You can unit depth. So 2R. What is this? Pi R, correct. Two by pi R. Okay. Such problems occur, okay, cooling of equipment, or you are putting a shroud, you have some electronic equipment, your configuration may be like this, you may have some electronic chips, and then this you may call 1, 2, 3, 4, then you have to get view factors and all that, okay. In ISRO and all that, they frequently enclose this electronic equipment with shrouds and all that, but this may not be of this shape, but okay. So to protect it from wind, dust and okay. Now this basically all these are warming up exercise. Eventually our goal is to do the enclosure analysis. Okay, so okay, I have a configuration like this. So vacuum, this plus this is 1, this is 2, get all view factors. $45 no, no, correct, yes. What is the included angle? 90, very good. So radius, of course, needless to say, radius is r. You convert the problems appropriately for the given configuration with unit depth, determine all view factors, okay, get all Vs. F11, F11, very good. A1, very good, 2R. A2, 2 pi R, okay. 3/4 of pi d, correct, into F21. Four by 3 pi, yeah. You can substitute for pi 3.14 and simplify all. Okay. So like that, you exploiting algebra, we can keep on solving problems, but we have to take a call and we have to close the discussion on this. I am just seeing whether I am missing something. Okay. Now we will take up a problem where we will have to necessarily get the view factor by direct integration, but since direct integration of two finite areas will be very painful, for demonstration purpose we will take a simpler problem, but even a simple problem some fundas are required. You cannot just blindly use the formula. Okay. Let us look at a problem where you have to get view factors with first principle integration. I hope because we have worked at so many problems in the last few classes, as far as view factor algebra is concerned, I hope all of you should be comfortable by now. If you recall the problem where we got stuck up, you must always suspect a problem in which concave and convex surfaces exist. When both concave and convex surfaces exist together, you have to see whether something is missing, or that is those kinds of problems lead to our potential troublemaker. In any case, if you have a concave surface itself, it has to be handled with caution. Okay. Now Problem number 26. I have a differential area dA1, okay, or simply D1, okay. Okay, I have a finite area here. Does not look all right. I have a finite area here, a circle. This fellow, the height is h, okay. This fellow's outer radius is r naught. It is a circle, right? It will look like this. It is not an ellipse, okay. Now, so the problem can be posed as determine the view factor dF12 between a differential area above a disk and a finite disk of radius r naught. If you want, I will, okay. Determine the view factor f d1 dash 2. Why did I say d1 dash 2? That 1 is a differential area, so I qualify it as d1 dash 2, or else you can take it as dA1 into A2, whichever way. So determine the view factor dF d12 between a differential area above a disk and a finite disk at a height of h, and a finite disk at a height of h from dA1 having a radius small r naught, okay. You do not have to worry about dA1 what is area and all, because it is a differential area. A2 I have given. What is the formula for view factor from a finite area to from an infinitesimally small area to a finite area? So f dA1 or integral over A2 is it correct? Yeah, this is what we derived. Now you have to convert the watch very carefully, you have to convert the problem into one in which the variable is small r. That small r can take a value 0 to r naught. Therefore, first you have to take an infinitesimally small area on that disk. Take an element, take a thickness of dr, so that area will be 2 pi r dr. Wherever dA2 is there, you can put 2 pi r dr. Okay. Then if it is at a radius r, from fundamental trigonometric principles you can find out what is that capital R squared, that will not be equal to h, right. From the disk to this it will be root of h square plus r square, and the limits of the integration small r can go from 0 to r naught, okay. It is, the problem is not over. Cos theta a and cos theta j you have to represent in terms of h, r naught, whatever. If you do all this, you can accomplish the integration. You can do it in 10 minutes. Can you start? Okay, then finished or? Is the problem clear? So what do you do first? this got dr. Okay. Now what is that and what is that? Cos theta I or theta I, yeah, 1, okay, theta 1 theta 2, okay. What is this? First theta 1 equal to theta 2 and we can just call it as theta, right? Theta 1 what is cos theta? R by no is R
h by root of
no first R equal to cos theta equal to h by capital R, very good. dA2 equal to dA2 equal to 2 pi R dr, very good. Okay, 1, 2, 3, 4, 5. Substituting for cos theta R and dA2 in equation 1, we can get what is the limit of the integration for R? 0 to R naught, very good, 0 to R naught h squared by R squared pi R squared, is it correct? Uh, 2 h squared what is R itself? Root of h square plus R square, right? Huh? Anirban, is it okay? Okay, let us assign some numbers. Yeah, you can directly integrate or you can still use first principles integration. You can do substitute in terms of R sin theta. What I will do basically is let R square plus h square be y, okay. Therefore, so I will have a half, is it? Huh? yeah, no, h square, yeah, by 2, by 2 y square. Okay. Uh, This is correct? Whole minus? Okay. Something is wrong. Yeah, yeah, it's fine. So this minus minus will get cancelled. Yeah, so you got an elegant result, but please remember one is infinitesimal. If both are finite areas, it will become difficult, and if it is not regular disk and all that, it is going to be very tedious. So lot of people in the 60s, 70s and 80s, different groups in the world worked on developing view factor relations, solving these integrals. It was considered a very important activity, because the view factors are repeatedly used in the radiosity calculations, also in multimode heat transfer problems. So view factors were also one of the reasons why double precision was invented and all that, right. You need view factors up to 7th decimal or 8th decimal accuracy, because if you have 100,000 view factors, you just can't leave with 2nd decimal or 3rd decimal. When you are doing a convective solver, if it is a convection and radiation together, then it will lead to lots of errors. So lots of people will, you can see papers where papers by Feingold, then SPV has written papers on accurate determination of view factors, and where they look at 4th decimal, 5th decimal, 6th decimal and all that. Okay, so view fact, so a lot of groups are preoccupied with the determination of view factors, but now with the computational resources becoming more powerful and more programs being available, and software like Fluent directly using this radiation, this activity of researchers is not that prominent nowadays, because these are considered as well settled problems. I mean, we know how to get view factors. There are of course still few situations, for example, you want to do a static testing, for example your GSLV or PSLV, you put it horizontally, you hold it somewhere and you do firing in Sriharikota, then when it is generating hot gases, what is the radiation load on the nearby structures, on the electrical cables, wiring, nearby men, material and all that. For that you will have to do all this view factor analysis, radiosity and all that, and find out. Okay, so this regularly the testing takes place. Okay, before launch you will have to find out. Okay, so they will test all these motors in Sriharikota, because basically that is the place where what is it called? Satish Dhawan, Satish Dhawan Launch Center or Research Center, whatever. Satish Dhawan Space Center. That's where they do all this launching business. Okay, so for all these space related things, this radiation becomes very, very difficult. Okay, for example, now we are looking at the lunar model and all that, right. We want to put a man on moon and all that. For the lunar model also, you will have to keep the pressure at 1 bar, you have to keep the temperature at 18 to 24 degrees centigrade. Then there will be nearby electronics and all that, then there will be solar radiation onto this spacecraft, okay, and electronics will be there. Then you have to do cooling calculation, you have to do heat load calculations. There it is again radiative heat transfer, which will be very, very important. Okay, so in all these exotic and fancy applications, it is eventually the radiation alone that matters, convection is not there. Okay, fine. Now what is the physical interpretation of this? When R naught is much small or when H is much larger compared to R naught, of course when H is infinite F will be 0, okay, right. Infinitesimally small disk, when some other disk let it be at a few thousand Kelvin, if it is infinitely far off then it has no influence. But if R naught by H is much less than 1, we can reduce it to R naught squared by H squared, okay, and it confirms the basic thing like the view factors, it goes as inverse square law, right, it goes inversely as the square of the distance between the two, 1 by H squared, H is the distance between the two, okay. So that is one indirect validation for this. Now so far we restricted our attention to 2-dimensional surfaces. It is nice to work with 2-dimensional surfaces because we can show it in the, we can demonstrate it in the classroom, you can solve some simple problems, it will boost your confidence and you are very happy that you are able to solve all these problems and all that. But unfortunately most of the real life surfaces 3D surfaces. Once you have 3D surfaces, just by algebra you cannot get because of the sheer finiteness. Therefore people have developed elaborate techniques. One of the most important techniques is called the contour integration, okay. dA1 is dx1 dy1, dA2 is dx2 dy2, therefore 4 integrations are involved. So they consider elemental strips on A1, elemental strips on A2, and then they will find out cos theta I, cos theta j, integrate it and do it. It is not a great thing, but basically the question of labor and the computational cost, okay. So these are fortunately available in the form of charts, okay. I will distribute the charts now, we will solve 1 or 2 problems with the charts, okay. Okay. So please look at these charts. So one view factor is view factor between 2 parallel rectangles, okay, and the second one is between 2 parallel discs, and on the back side we will have perpendicular rectangles, okay. These are some 3 simple configurations, you can do other configurations also, but with this simple configuration if you have a perpendicular rectangle and parallel rectangle then you can solve a furnace problem, right. If it is a cuboid or something, all are either parallel or perpendicular, then other view factors you have to get by algebra, okay. Now as far as disk is concerned, if your furnace is in the form of a frustum of a cone and all that, you need from top to bottom, if it is unequal areas, general formula for unequal areas, 2 discs of unequal areas, equal area will be a special case. So there are some, so L by Ri will be on the x axis for the 2 coaxial parallel discs, then the other variable is basically Rj by L, please look at it carefully, right. If it is not okay you can make correction now itself, you are going to use it in the exam, quiz second quiz as well as the exam, okay, fine. Now let us use this and solve some problems. Twenty, 27. Let us consider 2 perpendicular rectangles. It is not really, I have not drawn it. So this is 1, this is 3, this is 2. Okay. 1 meter, 1 meter, are all the dimensions given? get F12. The beauty is F12 cannot be obtained directly from the charts. F13 to 2 can be obtained, or F2 to 13 can be obtained. Okay. So before starting off, you have to remember a very important thing, which is called the decomposition rule. Yeah, please look at the board. This is the decomposition rule. F2 to 13, 13 is a composite which consists of 1 plus 3 together. F of 2 to 13 equal to F of 2 to 1 plus F of 2 to 3. Okay. Now let us work on this. Agreed? Yes? Is everybody through with this? So the decomposition rule says that the view factor from a say one surface to a composite surface is equal to F2 to 1 plus F2 to 3. I just wrote 3 reciprocal relations. So I will substitute for 2 1 3, 2 1 and 2 3 from these equations, and let us see what happens. So F2 to 1 3 is basically A13, F13 to 2, correct? F2 to 3. How many of you did not follow what I wrote? I did not do any magic here. I assume that this is correct first. Then wherever F213 was there, I am writing F213 as A13 F13 divided by A2. F21 I am writing it as A1 F12 divided by A2. F23 I am writing it as A3 F32 by A2. Now a very profound result, please look at the board, this is where most students make mistakes. A13 F13 to 2 is A1 F12 plus A3 F32, okay. F13 to 2 here it is valid because it is originating from one surface to the remaining two surfaces, but if it is from 1 to 3 you cannot break it because 1 3 has got one area, okay. Are you getting the point? So A1 F132 is equal to A1, if you still want to use the decomposition rule it should be used like this, because this comes from basic energy balance, thermodynamics cannot be violated, okay. When you are using decomposition rule you have to be careful. Now solve the above problem, solve the problem with the decomposition rule, okay. Now let us take the chart. You have to look at the chart, view factor for perpendicular rectangles, okay. So what is Z by X? What is Z by X? 0.67, very good, okay. And then what else is there? Y by x, how much was it? 1 point, what is y? 4, no, oh, correct, okay. Now f I j will be f2213, correct? F of I j is f, what is the value? 0.1, okay. Did everybody get this? You are free to interpret the graph like this and use, otherwise also z, y, whatever, huh? You can take the whichever surfaces, alright. Now Vamsi, did you get? Tejas, all of you have the charts? Okay, Mahendra, did you get it? Nisha? Okay, 0.14 is all right. Now we know decomposition rule. F21 again from chart, correct? Sorry, F2 to 3. Yeah, for F2 to 3, what is the story now? Z by x is 0.33, y by x is the same. Okay, so F2 to 3 will be 0.7 means that we have to go home. 0.07, okay. Therefore, what is A2? But they are same, no? Yeah. Oh, I am sorry. So only 1 and 3 are the same. Okay. What is A1? 3 meter square. A2? 12. Therefore, is this correct? Huh? Point 28. Huh? Okay. Now we can keep on escalating. We can keep on escalating the complexity level. So, okay, we can take a problem. One, two, 3, 4, 5, 6, 7, 8. Get F1 to 8, over, quiz 2 over. Huh? But it is possible to get, right? Yeah, you have to. What you can do is F1, 2, 3, 4 to 5, 6, 7, 8 you can get, okay. Then F3, 4 to 5, 6 you can get, F3, 4 to 5, 6, 7, 8 you can get, okay. Then what happens is, then some fundas you have to use, Vikram, you have to watch this carefully. F1 to 8 is same as F2 to 7, that is called the law of corresponding corners. F1 to 8 is the same as F2 to 7, okay, if it is like this, if it is properly oriented, okay, and then depending on the size and all that. So now you can use your common sense and break down the complexity, and this of course is, I think Professor SPV's book on heat transfer, I think he has derived. We can also derive it from first principle, but it will be a long story, okay. We will solve one more problem on view factors, but that maybe I will reserve it for the next class. So I will give something more decent. So what did I put? Okay, 1, 3, 2, 4. Get F12. Leave the dimensions. How will you do the geometry? Can you work out the formula? 1, 4, huh? No, what I want, wait. I want 1, 4, yes. 1, 2, there is no fun. Get F1, get F14, get F14. Okay, so maybe we will start out. We will solve this problem in the next class, but just 1 or 2 steps we can do. So A, is it correct? Huh? This is a dangerous splitting, huh? No. Okay, this is 1, and then F13 to 2. Like that you can slowly write, huh? And 15 minutes I think you can solve. Can you solve it in 15 minutes? Problem like this in the quiz? Yeah, not this corresponding corner will be difficult. Or I can give you a furnace. Furnace, I can divide it. I can ask you to find the view factor from this bottom to this top. Practical problem. One side is heated, other side you are keeping some material for heat treatment. What is the view factor? Okay.